I could just start saying that so Vienna was the place in which I made my first postdoc. So I'm always coming back here in this place with pleasure. So also for this reason, I'm thankful to the organizers for inviting me here. And not only because I like Vienna, but also because, thank you, the conference, the workshop is very interesting. And I learned a lot, for instance, that the structure factor matters. Thank you. And I learned also about viruses and of COVID viruses. So I am very interested. My name is Franco Ferrari from the University of Szczecin in Poland. My co-workers are Neda Abbasi-Taklimi and Marcin Piontek and L.Tubiana from the University of Trento. I'm going to talk about a topic that is very similar to what Chris has made, so thank you very much for the beautiful introduction. So what happens here? I'm really unlucky. So maybe I should do that. Maybe this. Oh. Look like this. Now. I'm not lucky with a little bit like. Okay, thank you. Oh, thank you. So I'm using a Monte Carlo code that is based on the Wong-Landau algorithm. Since I don't know if everybody here is acquainted with Wong-Landau. So the idea is simple that we are sampling polymers in the microcanonical ensemble. So the energy is considered and not the temperature. Then, of course, when the simulation starts, the system will start with conformation that are very probable. So they correspond to the most probable values of the energy. But every time an energy level is found, the Hamiltonian is corrected in such a way to make the probability of this probable energy state less probable. So at the end, this Wong-Landau algorithm arrives at a distribution of so a histogram or probability to find states with a given energy that it is uniform. So this is the black line on the top. Then using the corrections of the Hamiltonian, one subtract those corrections to the uniform distribution and one get the real density of state. So the density of state is this G. So this is some overall conformation, polymer conformation X. Hx is the Hamiltonian, and this Dirac delta function enforces the condition. Why it is going up? This is really, you should go back. Okay, so enforces the condition that the conformations have all the same energy. Then one can compute a lot of observables. Of course, I don't know if the structure factor can be computed very easily, but this is another problem. I will think about that. Thank you for making me aware that this is important. And however, the strength of the Wong-Landau is that once we compute this density of states, all temperatures are available. So one doesn't need to make a Monte Carlo simulation for each temperature. it is just essentially a Laplace transformation to go to the space in which there is the temperature, and beta is 1 over kb t. So, however, the price that has to be paid is that the potentials, just to speed up the calculations, the simulations must be simple. However, Raffaello Potestio and co-workers, they use this Wong-Landau also for more refined potentials, and to study in particular the energy landscape of proteins. Here we do something more, because not just the energy landscape, but everything. So not just the minima, but everything. So, and the idea is that, of course, this infinite here is just because we don't want crosslinks. I must say that at the moment we are on a simple cubic lattice, and epsilon is a bonus or a penalty that happens. So penalty if the interactions between the monomers are repulsive, and is a bonus if they are attractive. So epsilon can be used, and this happens. So there is a bonus or a penalty everywhere we have what we call the contact. A contact is just here. So whenever two monomers are near and their distance, so the monomers must be not contiguous, and their distance is equal to the smallest unit of length in the lattice, then we count a contact. So these are very short interactions, so we don't see the glass transition that you have seen. And we use something similar to what Christos has said. So we use the threading just to enforce the topological constraint in an exact matter. In an exact manner. So we started from a seed conformation, then we check threading, and if there is no threading, the conformation is accepted, otherwise it is not accepted. So the program underwent several tests, for instance, the existence of the theta point. This is in the case of homopolymers, the thermodynamic limits when the length of the knot is going to infinity to become very large. And so despite the fact that these potentials are very simple, one can study models that are important in physics. For instance, so let me explain. So this is epsilon. Epsilon here is always positive. However, attractive and repulsive interaction or neutral are enforced by these TAABB and TAB coefficients. They are just 1, -1, or 1, and they make epsilon, for instance, if TAA is -1, then A and A. So we have two types of monomers, A and B, though one can add other types of monomers. And here we have -1. This means that AA attracted themselves. So this is what is called, I think, the HP model used in proteins. Here are what it is interesting for this conference. So these are Coulomb interactions. A repel A, B monomers of type B repel monomers of type B, but A and B attract themselves, and the solution is implicitly enforced. And of course, so this is Coulomb because A and B attracted themselves, so they have different charges. Okay, so this is done. So the systems are also used to produce polymer knots, for instance, and And unfortunately, so I will not talk here always about these polyelectrolytes because they are difficult. So they are complex. And here you can see, for instance, so in black, there is the probability to find the lowest energy states in the case of a 4-1 knot with Coulomb interactions. On the other side, in red, this is a poly-4 catenane, so 4 rings concatenated, despite the fact that this is an homopolymer but in a bad solvent, and its energy levels go very low. Here we have minus 200, so we have minus 250 of the energy. Sorry, this is energy. It is not temperature. Sorry. So the energy can go very low in the case of the red one, but the probability for the polyelectrolyte system is 10 times in the logarithm scale, a factor of 10 in the logarithm scale smaller. So despite the fact that it is shorter. Okay, so, and in fact, I don't want to talk much about that because everybody, most of the person here knows about that, but polyelectrolytes, even in an ion solution with screened interactions, are very difficult to be treated. And if you see, if you use large random transformation to make the sampling, then you can see a potential that it is not the real one. If you use a small random transformation, you can see that here there is actually a point of minimum, which with large gauge transformations was not visible. However, in the case of a small random transformation, maybe one ends up, also, one can end up, so I don't know why, instead of the laser, I see, so it shifts, so the laser, maybe okay, maybe doesn't matter. So in the case of a small random transformation, the system can be trapped in one relative minimum and don't be able to exit from that. So this is something to be considered. And here, this is about the funnel-like structure. We also make a compression. So this is searching for the minima of a 3-1 knot with n is equal 4,320 monomers. And it is required that after every random transformation, the energy decreases. But however, if you do, so this is, sorry, the energy, the size, the gyration radius decreases. But if you do like that, naively, the simulation will hang, and so one should do that carefully. However, so we go exploring this energy landscape, and you see that here between 0 and 1,300, the system samples for a lot of times. You see, this is the histogram, number of explored sample for a given energy. So this is a lot of samples that are explored until here we arrived to the smaller energy configuration. So this is a polymer that has attractive interaction. Sorry, no, it is not attractive, but it is repulsive, but the number of contacts increases, so the size of the polymer decreases. And then there is which is not visible here because this peak is very high. Here in this area, up to 4,000 and something, we see other of these peaks, and this is compatible with a funnel structure in which first you have a large portion of the energy landscape, then it goes narrow. But first you have to explore everything to see this narrow. There are bottlenecks, and until you find the bottlenecks, the simulation is stuck. Then we go to another level, and this is funnel-like. This is also been recently discussed in this paper by Howe and others of 2025. So, so what can we do about with this code? Let's go to physical application. So, Wong-Landau is very good to study phase transitions, to have this phase diagram, to derive this phase diagram, and so far and so on. One can also add forces. And however, here I'm showing an interesting lamellar phase in the case of polyelectrolytes. So usually polyelectrolytes have lamellar phase. This is standard, but this is a lamellar phase inside a single knot. And so this is how the knot is made. It is two monomers of the A type, followed by monomers of the B type, followed by monomers of the A type, and so on and so far. And what here, if you want to have materials that are very stable thermodynamically, you see here that this peak is very high and very narrow. Usually we will see that peaks that are beyond the 1 are very rare. And also they are not narrow, they are broad. Okay, so I want to answer to a question that has been given here. So do the interaction of entropy origin due to the topological constraint interact or not with these charges, with the Coulomb interactions? So we study here a 4-plot, which is a system very simple. So these are two rings with a constraint. There are two minima and two maxima. And the reason to choose this very simple system, which is not entirely physical, but you see here that sometimes 4-plot appear in nature. So we use, so this is analytical result. And we use the Gauss linking number. And as you see, the Gauss linking number contains a magnetic field that are generated by fictitious current. So this is the formula of Gauss 200 years ago, more or less. They are generated by fictitious current that flow along the rings. So there are no other interactions. So we have only interactions of entropic origin due to the topological constraint, because this Gauss linking number is fixed to be a constant. And it turns out that the energy of such system can be computed exactly using field theoretical methods and using a very exotic transformation called the Bogomolny transformation. This interaction that contain magnetic field can be split in two parts. One, there are very short range interactions that can be attractive or repulsive, and they indeed started to interfere with the excluded volume interactions and also with Coulomb interactions, because as you see here, they can be attractive or repulsive. Plus, there are long-range interactions mediated by this magnetic field. And here, these very short range interactions are needed to prevent the line crossing, which would change the topology. And these other long-range interactions are they don't interfere with Coulomb, but they are used to preserve the global feature of topology. So we did also the computation of this system, analytical. It turns out that it has very interesting solution with conformal symmetries, relational invariance, and so far and so on. There are also connections with the GUI Chapman model and the Poisson-Boltzmann equation that are satisfied by solutions that minimize the total energy of the system. Then we tried also beyond the analytical calculations, also simulation to see what happens. And of course, we don't expect that we see this symmetries, conformal symmetries, because the energy, how much time I have? Okay. So because the energy landscape is full of minima corresponding to these analytic solutions, and it shifts during thermal fluctuations from one minima to the other. And of course, since we don't have interactions in the analytical model, the analytical results can be recovered while the temperature theta is large. So I forgot to say that it is a dimensionless temperature, and we can have also some input in this way from chemistry of the system. So, so here this we can skip. This is the poly 2 catenanes. This is a little bit not vertical, but I can assure that it is vertical, this system. It is along the z direction, because to have this constraint that we have only two maxima and two minima, these are in the z direction. Here the orientation is different, but it is just for convenience of representing and the system. And you see that the heat capacity, this is the specific heat capacity, is very small. It is not 25, it is 1 or less, and the peak is broad. So let me go. So this is, we can also study the conformations using contact maps between sectors of the sectors so we divide the polymers in the different sectors, and we can see how the sectors interact between themselves in the average. Then we have also a poly 4 catenane, and maybe so we have here, as you see, two peaks in the heat capacity with in the middle something that it is intermediate state. And this is, even if this cannot be seen, here it is ordered. So this is a bulk containing the attractive part. And here there are dangles that are the monomers of the four rings that are subjected to repulsive interactions. Here is the same, but the structure is no longer ordered, is no longer in the form of a crystal. Here we have an expanded state. So finally, so I want to conclude, but this is, so I would like to talk, of course, with crystals. We also have studied the polycatenanes. We have twist, of course. So in this case, there is, however, no twist. This is the heat capacity. And however, if you have rings, so I want to ask you, if you have rings that are not completely or almost rigid, it is very difficult to compute the twist. So how can one done? But we see also the white Fuller, sorry, what is white Fuller and Calugariano, yes. So let me conclude if I have still time. One results is that it has been possible to understand the role of the entropic interactions due to the topological constraint of using analytical models. Wang-Landau-based simulations allow to characterize the phases of single knot and catenanes of proteins using, however, these simple models like HP model RNA. This is a AB model, and we have also seen that polyelectrolytes, but with very short range interactions. I want to invite you to see also the poster by Neda Basi, which discusses other systems with other connections with the work of Christos and of course with Roman and also with Christian Micheletti. I don't know if I can do an advertisement. So I suggest the physical reports for people that wants to know more about this topic that is by Luca Tubiana and others. This has been published in Physics Reports. The title is Topology in Soft and Biological Matter. Here we have several authors of this report. So Christian Micheletti, Christos Likos, myself, and of course there was also Rudy Podgornik, which unfortunately died. So thank you very much.